Okay, to show how we do the analysis, we will analyze this circuit. So we'll do this calculation. So for this example, we will do the first step is the DC analysis. Okay, this is for our revision, and then the second step is the AC analysis midband. The third analysis is the low frequency AC analysis, and then last one is high frequency analysis. Okay, let's calculate the DC analysis. The objective of doing the DC analysis is to calculate the Q point or operating point of the transistor. So what is the operating point? Operating point is simply the parameter values. For example, the IDQ, the drain current, and we also have the VGSQ and VDSQ. So it depends on what are the parameters that you want to calculate. So for example here, we want to calculate IDQ. So this is IDQ is the current flow at the drain or the source. So remember that in MOSFET, the gate current is 0. So the drain current is equal to source current. So IDQ. Okay. So in order to do the DC analysis, the K value need to be you need to know the K value, and you need to know the threshold voltage. Okay, how we do the DC analysis? Okay, if the first step is you need to remove the capacitor. So for it at the DC, so at DC, the impedance of the ZC is very high. Okay, so it is open circuit, so you can remove this part. Okay, so you will only see the bias circuit. Okay, so next, what you do is, because this is the voltage divider circuit, you need to transform to the using the Thevenin theorem. Okay, so for the DC analysis, you need to write down two equations. The first equation is the transfer equation, transfer characteristic of the MOSFET, and then the second one is the KVL at input loop. Okay, so for the second part, the input loop is need to passing the gate and source. This is the gate and this is source, so need to pass this current path. So what we'll do is we transform this circuit. So we will have the R1 and R2 here. Okay, can be using the Thevenin. This is your V Thevenin. This is your R Thevenin, and it is connected to the RS. Okay, so our interest is only at this loop. Okay, so current at the R Thevenin is IG, and the gate current is equal to 0, and current at the RS is ID. Okay, so for the second equation, okay, let me put the second equation, the KVL. The KVL is the V Thevenin in this loop, in this loop. Okay, before that, we need to calculate the V Thevenin and R Thevenin. So what is V Thevenin? V Thevenin is the division between voltage division at 80 kilo ohm or R2. So this is 80 kilo over 80 kilo plus 100k times the total voltage is 15. So this is 6.67. This is 6.67. Okay, and then for the R Thevenin, this is the parallel R1 parallel with R2. So this is 80k parallel with 100k is equal to 44.44 kilo ohm. Okay, so the KVL will looks like this. We have the minus, the V Thevenin is minus 6.67 plus IG RTH 44.44k plus VGS. So do not miss the VGS. Between two terminals of the MOSFET will have the voltage drop, because between the gate and source we have the VGS. And then we have the ID. The RS here is 1k equal to 0. So the VG is IG is equal to 0, so this term is 0. Okay, this is the second equation. Okay, for the first equation, transfer characteristic is ID over K VGS minus VGS TH square. So K is already given as 1 milli and VGS TH is 1 milli and VGS TH is 2 volt. Okay, so we have these two equations. Okay, from this equation number 2, you can get the ID equal to 6.67 minus VGS over 1K. Okay, this is the from the second equation, and then this is equal to the first equation, which is 1 milli VGS minus 2 square. Okay, so you solve this equation, you will get the quadratic equation, VGS square minus 3 VGS and minus 2.67 equal to 0. So the solution for this quadratic equation will have two solutions. The solutions are VGS equal to 3.72 volt or minus 0.72 volt. Okay, you need to choose which one will be your valid answer. So the valid answer need to be the value that is higher than the threshold voltage, because we need to turn on the transistor. So this will be your valid answer. So from this valid answer, you can calculate the IDQ from this second equation. So this is 6.67 minus 3.72 over 1K equal to 2.92 milliampere. Okay, so this is the solution for the DC analysis. Okay, so we have done the DC analysis. The second question is the AC analysis at the mid-band. We want to determine the gain V out over V in. Okay, for the mid-band analysis, we start from with the drawing of the equivalent circuit at the mid-band. So this is the equivalent circuit. V signal, and this is R signal. You have here, this is your R1, R2, VGS, RD, RL. So where is the V out? V out is across the RL. So here, and then V in, where is the V in? V in, it is at this point. So V in. Okay. We have the parameters called GM. What is GM? GM is transconductance. So this is transconductance GM. So GM is equal to 2 square root KIDQ. So the K is given 1 milli, and then IDQ, we have calculated the IDQ in the previous calculation, 2.92 milli. So this gives the GM value of 3.42 millisiemens. Okay. Our objective, we want to calculate the AV. So AV is V out over V in. So first we derive what is the V out. V out is the current that across the RD combined with RL times the RD. So this is minus GM VGS. So minus GM VGS RD parallel with RL. So GM is minus 3.42 milli VGS so this is minus 3.42 milli VGS. Okay, RD is 2K, RL is 2K. So 2K parallel with 2K. So this gives minus 3.42 VGS. For the V in, so the V in is equal to VGS. So at the end, AV is equal to minus 3.42 VGS over VGS. This is minus 3.42. This is the mid-band AC analysis. Okay. The third analysis, we have done this first one. This one is done. The third analysis is the low cutoff frequency. Okay, at low cutoff frequency, the coupling and bypass capacitor will affect the performance of the amplifier. So the equivalent circuit will look like this. So this is your V signal. And then this is your R signal, C1. Okay, let me combine the R1, combine with R2. This is the RS. This is your CS. GM VGS. So remember to label all of the important component. This is the RD. This is the RL. So this is your C2. Okay. So this is the low frequency. So for the low frequency, we will use the common equation is FC equal to 1 over 2 pi RC. So we will do one by one each capacitor, and then we need to consider each impedance at the capacitor point. Okay, so what we'll do, for example, if you analyze the C1, the contribution of the C1, we assume the CS and C2 is short circuit. Okay, when we consider the analysis for CS, we assume C1 and C2 short circuit. And then lastly, if we assume the C2 is when we analyze the contribution of C2, we assume the CS and C1 is short circuit. Okay. So we have three cases. The first cases is cutoff frequency due to the C1 only. Second is due to the C2 only, and the third one due to the bypass only. Okay. For each cases, we need to have this RC circuit. So this is your R and this is your C. R and C. Okay, let's consider the FLC1. FLC1 is the low cutoff frequency due to the C1. So what happened is this CS will short circuit and then RS will not appear here. C2 is short circuit, so this is connected. So no, there will be no RS. So the impedance here, this is the ZI. For this case, the resistance is ZI plus R signal. So ZI and R signal is in series. So the combination is RZI plus R signal. So what is ZI? Because RS is bypass. So we only see the R1 parallel with R2. So the ZI is R1 parallel with R2 plus 300. So 300. So R1 parallel with R2, we know the value is 44.44K plus 0.3K. So this is 44.74 kilo ohm. Okay, for the capacitor C1, okay, C1 is given. So C1 is 10 microfarad, C2 is 1 microfarad, CS is 2 microfarad. Okay. C1 is 10 microfarad, C2 is 1 microfarad, and CS is 2 microfarad. So the FLC1 is equal to 2 pi R is 44.74K and then C is 10 micro. This is 1 over. So this will give you the FLC1 is put here, this is 0.356 Hz. So this is your FLC1. Okay, for FLC2, so this is the coupling capacitor at the output. So for this case, the R1 and R2 will not appear when we consider the Z out, because in this case we consider the CS is short circuit and bypass. This bypass, so the resistor is R is equal to Z out plus RL. So Z out is equal to RD. So this is 2K plus 2K. This is 4K. So FLC2 is equal to 1 over 2 pi times 4K times the capacitance is 1 micro. So this value is 39.8 Hz. Okay, this is FLC2. Okay, so the last one is FLC3. FLC3, the resistance is this is the RTH. Okay, RTH at S. Let's say I put it RTHS. So what is RTHS? RTHS is the resistance, equivalent resistance seen from this point. So what you will see is from this point is RS, and then the RS is actually in parallel with the impedance at the source. I call it ZS. Okay, this is similar to the calculation of output impedance for the common drain. For the common drain configuration, the calculation of output impedance, this is similar to that. Okay, this is similar to that calculation. Okay, RTHS is equal to RS parallel with ZS. Okay, what is the ZS? Okay, so the ZS, okay, please refer to the common. So refer to analysis of common drain, the output impedance. Okay, so you will get the ZS is equal to 1 over GM. So this is the RS is 1K, GM is 3.42 milli. This RS is 1K and GM is 1 over 3.42 milli. So this is 1K parallel with 292.4. So this will give you 226 ohm. At the end, the FLCS. So this is CS, not CT. CS is equal to 1 over 2 pi. The resistance is 226. And then the CS value is 2 microfarad. The value is 352 Hertz. Okay. After you have calculated all these three possible cutoff frequency, you can summarize it. FLC1 is equal to 0.356 Hz. FLC2 equal to 39.8 Hz. FLCS is equal to 352 Hz. So which one will be your dominant? Dominance means the actual cutoff frequency. So the dominant cutoff frequency will be, we need to choose the highest among these three values. So the FL will equal to 352 Hz. So this is the answer for the low cutoff frequency analysis. Okay, the last analysis is the high cutoff frequency. So high cutoff frequency, this is given, the CGD is 10 picofarad, CGS is 100 picofarad, CWI is equal to CWO 5 picofarad. Okay, so let's put here, CGD is 10 picofarad, CGS is 100 picofarad, CWI equal to CWO equal to 5 picofarad. Okay. For the high frequency analysis, the equivalent circuit, we need to draw the equivalent circuit. Equivalent circuit need to consider this 1, 2, 3, 4. 4 parasitic capacitance. Okay, this is your V signal, R signal, And then at the input, you have the CWI. And then you have this one is R1 parallel with R2. Between gate and the source, okay, the source is grounded here. This is the bypass. So this is grounded. Between gate and source, we have the CGS. So this is a VGS. You have the current source, GM, VGS. Okay, between the source and drain, it's not mentioned the value, so you can ignore the CTS. So we have here, this is your RD, and then at the output, we have the CWO, and then lastly, we have your RL. Okay. Do not forget the CGD. This is your CGD. Okay, so this is the high frequency equivalent circuit. Okay, for the high frequency analysis, you need to analyze separately the input side and output side. This is the input side, and then this is the output side. Okay. And then you may notice that we have one component. This is the CGD. CGD connecting the input side and output side. So this is what we call a feedback. This is a feedback capacitance. Okay, to eliminate this feedback capacitance, we need to replace it with the Miller input capacitance and Miller output capacitance. So what will happen if we remove it and replace with CMI and CMO? What is CMI? CMI is the Miller input. This is equal to 1 minus AV CF. In this case, CF is CGD. Okay, so the gain is minus 3.42. So CF is CGD is 10 picofarad. So this is 44.2 picofarad CMI. For the CMO, this is AV minus 1 over AV CF minus 3.42 minus 1 over minus 3.42, then pico will give you the value of 13 picofarad. Okay, so we have the CMI and CMO. So when you replace the CGD with the CMI and CMO, your equivalent circuit will looks like this. So this is the CWI. This is R1 parallel with R2. This is your CGS. VGS, okay. And then here at this input, we'll have the CMI. Okay. And then at the output, you have this one is CMO. This is your GM, VGS, RD, CWO, and RL. Okay, so you have the clear division between the input port and output port. Okay. So next is the calculation. So the calculation use the FC equal to 1 over 2 pi RC. So for the input side, FHI, so the resistance is equal to, you see here, R1 parallel with R2 is parallel with R signal. So this is R1 parallel with R2 parallel with R signal. So R1 parallel with R2 is 44.44K, and then R signal is 0.3K or 300. So this is, the value is 298 ohm. Okay, for the C is the total of all the capacitor in the input side. Capacitor is CWI parallel with CGS. This is the CGS parallel with CMI. So the parallel capacitance, you need to sum up all the value. This is your CGS plus CWI plus CMI. Okay, CGS is given as 100 picofarad. CWI is 44.2. Oh, sorry, this is not CWI. CMI. Okay, CWI is actually 5 picofarad. CMI is 44.2 pico. So this gives you 149.2 picofarad. So the calculation, FHI is equal to 1 over 2 pi 298 and then 149.2 pico. So the value is 3.58 megahertz. See, this is the input side. For the output side, FHO, for the output side, the resistance here is the combination of the RD and RL only. So RD and RL is in parallel. So this is RD parallel with RL. So this is 2K parallel with 2K equal to 1K. For the capacitance, the capacitance in the output at the output side is CMO and CWO. Two capacitance only. So this is CMO plus CWO. So CMO is 13 picofarad, CW is 5 picofarad. So this is 18 picofarad. Okay, so FH out is equal to 1 over 2 pi 1K 18 pico. This is 8.84 megahertz. At the end of this analysis, you need to choose the dominant cutoff frequency. Dominant FH. So the dominant FH is the one, the lowest value between these two frequencies. So the FH equal to 3.58 megahertz.